In today's assignment, we are going to look at metal semiconductor junctions. This is assignment 4. So, in class we looked at two kinds of metal semiconductor junctions. One was the Schottky junction or the Schottky contact, and the other was the ohmic junction or an ohmic contact. So, we saw that a Schottky junction forms when the work function of the metal, so phi m, is greater than the work function of the semiconductor. In the case of an ohmic junction, it is the reverse. The work function of the metal is less than the work function of the semiconductor. We also saw that a Schottky junction essentially behaves like a rectifier. So, it conducts the current in the forward bias and does not have any conduction in the reverse bias. So, in this way a Schottky junction is similar to a PN junction, which is also a rectifier. An ohmic junction, on the other hand, from the name, is just a pure resistor. It conducts both in the forward and the reverse bias, and the conductivity is defined by the conductivity or the resistivity of the semiconductor material. So, in today's assignment we will be looking mostly at Schottky junctions. We will do some calculations on the Schottky barrier, the contact potential, and also the current in the forward and reverse bias. So, let us go to problem number 1. So, we want to show how a Schottky junction is formed between a metal and a p-type semiconductor. So, we can do this by sketching the band diagram under equilibrium, forward and reverse bias. So, in class when we looked at the example of a Schottky junction, we looked at a metal and an n-type semiconductor. So, let me draw that first under equilibrium, and then from there we will look at a metal and a p-type semiconductor. So, we said a Schottky junction is formed when phi m is more than phi semi. So, we will start with the metal here. So, let me just draw this slightly up. So, this represents the vacuum level. This is the Fermi level of the metal, and this space is the work function of the metal. So, all the energy levels below this are completely full. So, we will start off with an n-type material. So, this is your n-type material. You have EC and EV. So, EV is the valence band and EC is the conduction band. It is an n-type. So, the Fermi level is close to the conduction band. Once again here the distance between the Fermi level and the vacuum level is the work function of the semiconductor. So, when these two are brought together in contact, we know that in equilibrium the Fermi levels must line up. So, we have excess electrons that are there in the conduction band of the semiconductor. these will go and occupy all the empty states in the metal. So, there is a net positive charge on the semiconductor side, a net negative charge on the metal side. The electric field goes from positive to negative and the bands bend up in the direction of the field. So, if you were to draw this under equilibrium, so I will just mark my junction. This is EF. So, this is my metal side and this is the N type semiconductor. This is the EF of the semiconductor. So, far away from the junction, the semiconductor will still be N type. So, let me draw the bands slightly closer. So, this is N type EC and EV. There is a net positive charge on the semiconductor, a net negative charge on the metal, and the bands will bend up. So, this in turn forms the depletion region. And this is the band diagram at equilibrium. So, this is a case of a metal and an N type. This is similar to what we saw in class. So, let us now draw one for a metal and a P type. So, once again we have the vacuum level. You have the Fermi level of the metal, and this is phi m. So, this is the metal. We now have a P type semiconductor. So, this is EC, this is EF, and this is EV. So, it is a P type semiconductor, so that the Fermi level is close to the valence band. So, we can use the same argument that we used for a metal and an N type, except now that the argument is reversed. So, once again when the junction forms, the Fermi levels must line up, but instead of excess electrons going from the semiconductor to metal, we now have the electrons moving from the metal to the semiconductor, or the holes moving from the semiconductor to the metal. So, that there is a net positive charge on the metal side, a net negative charge on the semiconductor sides, and bands will bend down as we go from the semiconductor to the metal. So, this if we draw in equilibrium, the Fermi levels must line up. So, I will put an interface. So, EF and EF, metal and P type semiconductor. Far away from the junction, your material is still P type, and then the bands bend down, so that there is a net negative charge and a net positive charge. And this is the depletion region. So, the band bending here is similar to that of a metal and an N type, but it goes the other way. So, we now want to draw the energy band diagram in forward and reverse bias. So, in the case of a forward bias, so this is my metal, this is my P type. The metal is connected to a negative charge, the p type is connected to a positive charge. So, in this case the Fermi levels shift and the barrier essentially is lowered. So, we can once again draw this, that is my interface, that is my metal. Now, the Fermi levels no longer align, and for the p type the Fermi level is shifted down. And this shifting down is given by your external potential, that is V naught. So, here the barrier for the motion of the electrons and holes is reduced, so that there is an increasing current when you apply an increasing voltage. In the case of a reverse bias, so M and P, the metal is connected to positive, the semiconductor is connected to negative. Once again the Fermi levels do not line up, but instead of shifting down the Fermi level is now shifted up. So, that is my interface. EV, EC and EF. So, this is the metal and this is the p type semiconductor. So, this is a situation where we have a metal and a p type in equilibrium. This is the energy band diagram, forward bias and reverse bias. So, let us now go to problem 2. In problem 2, we have an n type silicon with 10 to the 16 donors per centimeter cube. Now, n silicon with Nd is 10 to the 16 per centimeter cube. The two ends of the sample are labeled B and C. So, we have two ends. So, there are essentially two metals at the either end. So, if I were to draw a schematic, this is my N silicon and I have B and C on both sides. So, let me just shade them to show you that they are essentially metal contacts. The electron affinity of silicon is given. So, chi is 4.01 eV, and there are 4 potential metals which can be used for these contacts and their work functions are given. So, we have cesium, lithium, aluminum and gold, and their work functions are essentially given. So, the first thing we need to do is to calculate the work function for the semiconductor. So, we can draw an energy band diagram. So, this is vacuum, we are only drawing the semiconductor side, EC and EV. It is an n type semiconductor. So, the Fermi level will be closer to the conduction band. Now, the electron affinity is the energy difference between the conduction level and the vacuum level. So, this is essentially chi. We need the work function. So, we need psi of the silicon. To know that, we need to know the position of the Fermi level, and that can be calculated from the concentration of donors in the material. So, we can just say EFN minus EFI is KT ln of N over Ni. So, N is nothing but Nd, it is fully ionized. Ni for silicon is given, and we also saw this during the previous assignment, it is nothing but 10 to the 10. From this we can calculate the value of EFI minus EFN. So, EFN minus EFI we can calculate. We also know the position of the intrinsic Fermi level. So, we can calculate it from the values of Nc or Nv. In this particular case, EFI is given to be 0.55 electron volts and the band gap of silicon is 1.1. So, this whole thing is 1.1 eV. EFI is given to be the center of the band gap and this is 0.55. This distance is also known and the value for this is 0.192 0.357 sorry. This is 0.357. So, everything else is known except for this. So, EC minus EFN is nothing but 0.192. So, from this we can calculate the work function of the silicon. So, phi of silicon, since it is n type I will just write phi of n, is nothing but chi plus EC minus EFN, which works out to be 4.20 eV. So, if you look at the various parts of the question, part A asks which metals will result in a Schottky contact. So, we have a Schottky contact when the work function of the metal is greater than the work function of the semiconductor. So, those are essentially aluminum and gold. So, Schottky contact would be aluminum and gold. Which metals will result in an ohmic contact? So, an ohmic contact is one where it is reverse, the work function of the semiconductor is higher. So, it is just cesium and lithium. So, part C, sketch the IV characteristics when both B and C are ohmic contacts. So, let me draw that. So, B and C are both ohmic contacts. So, an ohmic contact is nothing but a resistor. So, when you have both B and C to be ohmic, then the whole thing just acts as a resistor. So, if B and C are both ohmic, then the whole thing is just a resistor. So, the IV characteristics will just be a straight line and the slope of this line will be just 1 over r. Part D, sketch the IV characteristics when B is ohmic. So, B is ohmic and then C is Schottky. So, we have one ohmic and one Schottky junction. So, in the case of a forward bias, you will have a Schottky junction will be essentially a high conductor. So, it will start to conduct. In this particular case, the resistance will be determined by the highest resistance point, which is your ohmic contact. So, here in the case of forward bias, so if you were to draw I versus V, you have a highly conducting junction which is junction C, and you have a resistor which is junction B. So, this will essentially behave like a resistor. In the case of a reverse bias, C is essentially reverse biased, so that there is very low conductivity through that. So, that will essentially determine the conductivity of the entire circuit, so that you have a very low conductivity in reverse bias. So, the same is true when B is Schottky and C is ohmic, the curve will be similar. In part E, sketch the IV characteristics when both B and C are Schottky. So, B and C are both Schottky. So, in this particular case, if one of the junctions is forward biased, the other junction will be reverse biased, and so on. So, whether you are in the forward or the reverse, there will always be one junction that is reverse biased, which will have very low conductivity. So, the IV characteristics in this particular case will be a very low current in both forward and reverse bias. So, this kind of a situation is very important when you are trying to make electrical contacts to a semiconductor. Usually we have to make two contacts. Ideally we want these contacts to be ohmic, because we do not want the contact itself playing a role in determining the IV characteristics, but there could be diodes based on the Schottky effect. These are Schottky diodes. In this particular case, you would want one junction to be essentially a Schottky junction and the other to be an ohmic junction. So, let us now go to problem 3. So, problem 3, you have a Schottky junction diode between tungsten and N type silicon. The silicon is doped with 10 to the 16 donors per centimeter cube. The cross sectional area is given. So, A is 0.1 millimeter square. The electron affinity of silicon is given, same as the last problem, 4.01 eV, and the work function of the metal is given to be 4.55 electron volts. So, once again we need to calculate the work function of the semiconductor. So, we can do the same thing that we did in the last problem. In this particular case, the effective density of states in the conduction band is given. So, that is 2.8 times 10 to the 19. So, we could use this directly to calculate the position of the Fermi level. So, N is nothing but Nc exponential minus Ec minus Efn over kT, from which you could calculate Ec minus Efn. So, N is nothing but Nd, which is your concentration of donors. Nc is given, everything else is known. So, Ec minus Efn is essentially 0.205 electron volts. So, from this you can calculate the work function of silicon to be 4.215 electron volts. So, we can draw this in a band diagram. So, I will just draw it schematically. This is my tungsten. Work function of tungsten is given, so 4.55, and this is my n-type semiconductor. So, EC, EV, this is 4.01, this whole thing is 4.215, and this is 4.55. So, again we have a case of a Schottky junction between tungsten and n-type silicon. So, part A, we want to calculate the theoretical Schottky barrier. So, we want to calculate phi b. Phi b is the Schottky barrier, and that is essentially the work function of the metal minus the electron affinity of the silicon. The Schottky barrier represents the barrier for the electron to move from the metal to the semiconductor side. So, you have an electron going from EF to the conduction band. So, this is just phi m minus chi SI, can put in the numbers, and this is 0.45 electron volts. Then we want to calculate the built in voltage. So, V naught is nothing but chi m minus phi SI divided by E. So, E is just to convert it from electron volts to volts. It is the difference between the work functions. So, this we can substitute, and the answer is 0.335 electron volts. In part C, we need to calculate the reverse saturation current and also the current when there is a forward bias of 0.2 volts across the junction. So, part C, we want to calculate the current in the junction. So, in the case of a Schottky diode, it is possible to write an expression for the current. This is something we did not see during the course of the lecture. So, we can write the current J as some constant J naught exponential EV over KT minus 1. So, V here is your external potential, J naught is your reverse saturation current, and J naught is equal to BE T square exponential minus phi b over KT. So, this is called a Richardson-Dushman equation. And it is actually used to calculate the current during thermionic emission from a metal. So, Be is usually a material constant, it is a property of the interface. So, whether you have tungsten and silicon or platinum and silicon, platinum and germanium, the value of Be will change. So, Be is a constant that depends upon the materials, which is basically it's a property of the junction. So, in this particular case the value of Be is given. So, Be is 110 ampere per centimeter square per Kelvin square. So, the value of phi b we calculated earlier, this is nothing but your Schottky barrier. So, from this problem you can calculate J naught. So, everything else is known, temperature is 300. So, from here J naught is essentially 8.5 times 10 to the minus 3 ampere per centimeter square. If you want to calculate the current, you multiply this with the area. So, current I is J naught times A, which is 8.5 times 10 to the minus 6 amperes or 8.5 microamperes. We can now calculate the current during the forward bias. So, J is J naught exponential EV over kT minus 1. So, usually the exponential term dominates. The external voltage is given to be 0.2 volts. So, we can substitute the numbers and J comes out to be 19.3 amperes per centimeter square, or the current I is just 0.019 amperes. So, this is the current during forward bias. You can see that it is nearly 4 orders of magnitude higher than the current during reverse bias. This is why a Schottky junction is essentially a very good rectifier. In part D, the question says that the experimental Schottky barrier is actually higher. So, phi b experimental is 0.66 eV. So, it wants us to do the recalculation. So, this experimental value takes into account the fact that the interface is never perfect, that you always have some sort of defects at the interface. So, if you use this, we can use the same calculations that we just did, except that now we have to use the newer value of phi b. So, in this particular case J naught comes out to be 8.3 times 10 to the minus 5 ampere per centimeter square, and current J is 0.19 ampere per centimeter square. So, the actual current is slightly lower than what we would expect if you use the theoretical values, but the important fact is that it is still 4 orders of magnitude higher than J naught. So, that your Schottky diode or your Schottky junction still functions as a rectifier. So, let us now go to the next problem. So, problem 4, we have a platinum silicide Schottky diode is fabricated on N silicon. So, you have platinum silicide on silicon. So, how this is usually obtained is by first depositing platinum metal. Usually it is done by some vapor deposition process like thermal evaporation or sputtering or e-beam evaporation. Then the interface is annealed, so that we have interdiffusion between platinum and silicon, which again react to form the silicide. So, depending upon the composition, you can get a single composition PTSI, or you could get multiple compositions, again depends upon the thickness of the platinum layer and the amount of intermixing. So, these silicide layers are usually formed by depositing the metal and then doing some sort of a post annealing treatment. So, in this particular case it is an N type silicon. So, Nd is 10 to the 16 per centimeter cube. The barrier height in this particular problem is given. So, phi b is 0.89 volts. So, one of the advantages of doing a post annealing is that usually eliminates some of the defects, so that your barrier is essentially very close to your theoretical barrier. So, once again we want to calculate. So, the forward current is known. So, J is given to be 2 amps per centimeter square, and we want to calculate the value of the voltage. So, V external is what we want to calculate. So, we can go back and use the same equation. J is equal to J naught exponential EV over kT minus 1. J naught is nothing but BE T square exponential minus psi b over kT. So, the value of BE for this problem, we can still take the same value, 110 ampere per centimeter square per Kelvin. So, we can use this and calculate J naught. So, J naught is just got by substituting BE T square and exponential of minus phi b over kT. Once we get the value of J naught, we can put the value of J naught here. We need to know the value of J. So, J is given to be 2 amp per centimeter square. The only thing that we do not know is V external. So, once we calculate J naught, we can plug it here and get V external. So, I will just write the answer. V external for this particular problem is 0.49 volts, but the calculation is very similar to what we did the previous problem. So, let us now go to problem 5. Problem 5, we have a Schottky diode formed by depositing gold, but now the material is N type gallium arsenide. So, we have N gallium arsenide with Nd is 5 times 10 to the 16 per centimeter cube. So, once again in part A, we need to calculate the forward bias voltage for a current density. So, J is 5 amps per centimeter square, and we need to calculate the voltage for that. So, this is again similar to the previous problem, except now the material is gallium arsenide. So, the first thing we need to do is to calculate the barrier potential. We are going to assume that it is a theoretical barrier. So, we need to know phi b, which is nothing but phi m minus the electron affinity for gallium arsenide. So, in this particular case, Eg of gallium arsenide is given, but more importantly we only need the electron affinity. This has a value of 4.07 eV. So, we can still use the other values to calculate the contact potential, but as far as part A is concerned, the only thing we need to know is the electron affinity. So, phi m is given to be 5 electron volts. So, this is the work function of gold. The electron affinity of gallium arsenide is known, so that the theoretical barrier potential is nothing but 0.93 electron volts. So, once we get that, we can calculate J naught. Again, for the gold and gallium arsenide interface, we can calculate, we have the values for BE. BE is equal to 45 amps per centimeter square per Kelvin square. So, BE is not only a material property, it also depends upon what facet of the material you have. So, whether you have a 100 plane or a 110 or a 111, that will also affect the value of BE. So, J naught is a number we can calculate, all the numbers are known. So, this is nothing but 9.1 times 10 to the minus 10 ampere per centimeter square. So, J naught is known, J is known, exponential EV over KT minus 1. So, again J is known, J naught is known, the only thing that is unknown is V, from which we get V to be 0.58 volts. In part B, we need to calculate the change in the forward bias voltage to double the current density. So, J new, which is your new current density, is 2 times of the old one. So, this should be 10 amps per centimeter square. You can either take the ratio of the old and new J, or you could use the same equation J naught exponential EV over KT minus 1, you can calculate. So, if you take the ratio J new minus J, which is 2, is equal to exponential EV new over KT by exponential EV over KT. So, V is known, we just calculated that in part A. The only thing we need to do is to calculate V new, and V new is 0.60 volts. So, in the case of a Schottky junction, which is essentially a rectifier, we have seen how to calculate the Schottky barrier voltage, the built-in potential, and also the current during both forward and reverse biased. An ohmic contact is much simpler. An ohmic contact is essentially a resistor, and the resistivity is usually given by the resistivity of the semiconductor material.